Now that we've taken sort of a tour of Scala's object-oriented features, we can come back to the calculator that we wrote previously and start to clean it up. The biggest candidate for cleanup that we left before was the fact that there was all this duplication in handle operator. Recall that we had to do this stack.pop stuff to get two operands off of the stack. Then we had to do stack.push to put the operation's result back on the stack. And really, the only thing that differed between these cases was the operation itself. In fact, even just producing true to say that yes, we matched a token, that was duplication as well. So we'd like to only write that once, and the way that we can do that is sort of by recognizing that we can represent operations as some kind of a class hierarchy. So let's create a trait to represent this. Operator. We could do this with an abstract class, we could make it sealed, that doesn't really make much of a difference. And we'll say that operator has a method called operate. Operate will just take two numbers and produce the result of operating on them. Now, just so that you don't have to watch me type, I'm just going to paste in implementations of operator that I've constructed already. We've got 4 of them: add, subtract, multiply, and divide. The operate methods behave the way that you would expect. And I've also got 2 string implementations here. Now, just to point out really quick, I've made these case objects just to demonstrate that that's possible. It lets you pattern match on the objects, for example. So now that we have these objects, we can construct a map that associates the tokens, the symbols, plus, minus, and so forth, with the actual objects that they represent. So I'm going to put them in the companion object for the operator trait. This is something we haven't talked about yet, but yes, traits can have companion objects. So we'll say object operator, and we'll construct a map like we talked about. Val operators is going to be a map from strings to operator instances, and it's going to be a map consisting of plus maps to the add operator, minus maps to the subtract operator, times maps to the multiply operator, and slash maps to the divide operator. Okay, so now we have our map, and we could use that to clean up handle operator. We could go ahead and just do that now, but I want to also observe one more thing, and that is handle operator looks kind of like a custom extractor in a way, because it's taking a token in, and it's trying to match the token. And if it matches, well, we're doing some stuff with the stack. You can sort of ignore that. But if it matches, we return true, and if it doesn't match, we return false. Same thing with handle number here. We're trying to convert the token to an int. And again, if you ignore the fact that we're pushing something on the stack as a result, it's, producing true if it was successful and producing false if it failed. So this looks kind of like an onApply method. So what I'd like to do is actually write those onApply methods and separate out the stack manipulation logic from the matching logic. Let's go add a method called onApply in the operator companion object. Def onApply. So it's going to take a token. That's the thing that we're matching on. And it's going to produce, well, onApply produces options, right? It's going to produce an option of operator. The way that we'll implement this is using a handy method on the map. We'll call operators.get token. Operators.get is perfect here because operators.get actually returns an option. If it finds the token as a key in the map, then it'll return the operator that's associated with the key. And if it doesn't find the token, then it'll just return none. So this is perfect. The other extractor that we need is a number extractor. Let's say object number. Again, we're going to define onApply to take a token. And this time we're going to return an option of int. Now, interestingly, we've written this code before when we talked about how to translate exceptions into options. We just wrap the result in a sum if it was successful. And if it failed, we just return none. So now we have two extractors that we can use in pattern matching. And they don't do any stack manipulation, and I think that that's good design. But of course that means we need to move the stack manipulation somewhere else. So let's go and take all this code that we are replacing and delete it. In the calculate method now, in our for loop, all that we need to do is match on the token. And we can use our custom extractors now. So case, let's say number. And again, recall that the way onApply works is it takes the token as input, and the thing that looks like a parameter here is actually the output. It's actually the return value from onApply. So in this case, it'll be some number. What do we do? Stack dot push num. Very easy. And in the case of an operator, again, it's taking a token as input, and the op here is an operator object instance. We can do the same thing we had before. Val RHS equals stack dot pop. Val LHS equals stack dot pop. And stack dot push. And now we have this factored out, so we can say op dot operate LHS RHS. Our last case was the case that we don't actually match a token. The token was garbage, so we'll still throw our exception here. Okay, I'll save this. I think that this code is much more readable as it stands than what we had before. And not just because we've eliminated the duplication, but also because, I mean, if you look at this, we're looking at each token. So for each token, we see if the token is a number, or if it's an operator, or if it's neither. We don't have that weird Boolean logic in the if else in calculate like we had before. I think this is readable not just for a Scala developer, but really for any developer. I think somebody could come in and look at this code and sort of have a good sense, not necessarily understanding all the details, but look at the calculate method and have a pretty good sense of what it does. So I'm pretty happy about that. I want to go back to SBT and make sure I haven't broken anything. Let's try running this with, let's just do a simple one. 1, 2, 3, plus, minus. That should give us -4. That's good, right? Because 1 minus the sum of 2 plus 3, that's -4. If I try to run this with garbage, it should throw an exception. That's what we wanted as well, right? We just wrote that again. So, pretty good. The other thing that I'd like to do, now that we've got our code a little bit cleaner, is expand the functionality of the calculator. Recall that at the beginning of Lesson 3, we talked about, well, the calculator really only does one thing. Really, it only knows how to parse an expression and just compute the value. But we said we wanted maybe to be able to convert our expressions to infix notation or whatever. So a very common pattern in object-oriented programming is something called the composite pattern. In Scala, we don't really use those terms. We just call the composite pattern common sense. But what we're going to do, no matter what you call it, is build a parse tree. So I'll define a trait called expression. This time it's going to be a sealed trait, because what we're going to make is an algebraic data type. Expression doesn't even need to contain anything necessarily. I think it's best if it doesn't. So we have two kinds of expression in our parse tree. One is going to be numbers, and the other is going to be operations. So case class number expression. And a number expression just represents the parse of a single number, so value of type int. And this case class is going to extend the expression trait. The other case class we need is the operation expression. And the operation expression is going to be sort of our composite case because it's going to have a left-hand side sub-expression in the parse tree and a right-hand side sub-expression in the parse tree, as well, of course, as the actual operator. So let's represent that. LHS is an expression. RHS is an expression. And we also need op, which is our operator. This is going to extend expression as well, pardon the long line. Okay, we have our parse tree declared, and this again is an algebraic data type, very simple, and we're not going to pollute it with any sort of behavior. You might guess that, well, if we want to compute the value of expressions, we should have a get value method or something like that in the expression trait. But we're not going to do that. We'll do it slightly differently. You'll see in a moment. The first thing we need to do is build these parse trees. And in fact, the code that we need to do that is really already here, because the calculate method is actually the core of our parser. So let's update the comment here. Parse a postfix notation expression. We'll rename this to parse so that we don't get confused. And parse is going to produce an expression. So the way this works is that we're going to be manipulating a stack not of ints, but rather a stack of expressions. When we see a number, instead of just pushing the int value, we're going to construct a number expression out of it. And in the case that we see an operator, well, we're not going to operate on two sub-expressions. We're just going to create an operation expression that contains the two, as well as the op that we've parsed. And that's the only change that we need to make to construct our parse tree. So I think we can pat ourselves on the back here for being pretty clever. But now the part where we're not so clever is we threw out calculate. So we need to do something about that. Let's make some space, and we'll define a calculate method. This time the calculate method should take parse tree. So we'll call expression of type expression. So if this were, let's say, Java or C++, the way that we would probably best implement this is using the visitor pattern. The visitor pattern is one of object-oriented programming's perhaps most notorious design patterns. And we won't get into details on it, but it represents the traversal of a recursive data structure, such as the expression parse tree that we have here, right? Because operation expression recursively contains instances of expression. Now, we don't need to use the visitor pattern in Scala because instead we have pattern matching. So we'll just match on the expression. Our base case is number expressions. Those are the leaves of our tree. And the value of a number expression is just the value that it contains, of course. And for an operation expression, it's more interesting. The result of this is going to be the result of applying the operator to the recursive calculation of the left-hand side and the right-hand side. Op.operate, and we'll recursively call calculate LHS and calculate RHS. Okay, pretty cool. Since we wanted to be able to do multiple things with these expressions, let's also just demonstrate one additional one. Def to infix. This one's going to produce a string, and we can use the same technique. Expression match. Well, converting a number expression to a string is just going to be the number itself again, so value.toString. And an operation expression, this is the interesting case. Just to show off a feature that came out in Scala 2.10, I'd like to use string interpolation to construct our string representation. We can say s, and quotes, and we'll say to infix LHS, op to infix RHS. You might think this is a little bit ugly. If you do, you can use string concatenation, but I think this is actually nicer than that. Finally, let's go back down to our main and finish this up. Let's say val expression is equal to parse args0. So now we can print line, and let's use string interpolation here as well, just for fun. To infix expression equals calculate expression. So let's save this and see how it works. Run 1, 2, 3 plus minus. Hey, there we go. It's parsed our expression, converted it into infix, and computed the result. So there we go. Our calculator is much more flexible now. And it was all because we created an algebraic data type to represent our expressions. Now, when we start getting into functional programming, there will be some additional cleanup that we can do. For example, our case objects here that we've defined, well, those really could just be replaced by simple functions. Another thing that we talked about before was the fact that we're manipulating a mutable stack. And we said that we generally prefer immutable data structures because we can reason about them more easily. And so we're going to end up using higher order functions to help us with that. But for now, I think we can be pretty proud of ourselves because we've implemented an object-oriented calculator that does more things than just one. And we managed to use some of Scala's special features along the way.